Alright. We're going to start where we left off last time, which is quantum number, huh? 29 or 30? 30, I think. 30, page 30. Yeah, I'm pretty sure we're done. Oh, now let's go to page 30 first, and we'll revisit page 29 and so on. We'll just try to remember again the rules of what is allowed versus not allowed state. So the numbers that we have here inside the brackets are essentially the quantum number n, which tells you the number of shell, quantum number L, which more or less tells you the shape, ML, which tells you the angle or the directions in which the orbitals are pointing, and the MS value is how the electrons are actually spinning. So, how about the first one here? Is this an allowed or not allowed state? We have the number 3, 1, -1, and 1. If it's allowed, say it's okay, and then if it's not allowed, what's wrong with it? ML is technically called the magnetic.
Okay, so the plus or minus.
Sorry? Somebody's trying to go in. Nope, I thought somebody was trying to open the door. Sometimes it's locked on this one.
Not allowed.
This one is not allowed. Which one is incorrect? The MS in this case, right? So MS value can only be plus 1/2 or -1/2. So in this case, the MS value is 1, so that's not an allowed state. So it could either be a positive 1/2 or just -1/2. So this particular state is not an allowed state. So it's like it's one of the key in a piano that doesn't actually exist. Right. So how about the next one? Well, actually, let's do kind of some process of eliminations. MS can only be positive 1/2 or -1/2. So you can see that for the rest of them, it should be all right, right? So MS will not be an issue with the rest of these things. The next one is wrong? Why? ML value? What's wrong with the ML value? Not quite. The ML value could go from -L to +L. So in this case, L is equals to 1. So it could go from -1, 0, and +1. So in this case, it's actually okay. Yeah. How about the next one? What's wrong with this one? That's right. So in this one, L must be n-1 or smaller. Right. So that's the wrong one. Actually, let me highlight that one. How about the next one? Yes or no? This is a no. The ML value is incorrect. So ML goes from -L to L. If L equals to 0, then you can't go anywhere else other than 0. ML should be 0, right? The next one here is also not allowed. It was the same reason from it was before, right? So this is not allowed. And the last one here is okay or not okay. That looks. This one is okay. It satisfies all the rules. So we get okay in this one. All right. So while we're at it, we're just going to try to get all the rules down, and then once we get all the rules down and the permutations possible, we're going to go back and look at the periodic table, and essentially they're telling you the same thing, that the periodic table is assigned and arranged in accordance to some of these rules as well. So just on this one, we're just going to label all the value possible for n equals to 2. Right, so if this is n, L, ML, ms. It's a tedious exercise, but once in a while it's useful to do these as well. So if n equals to 2, L, the smallest L possible could be 0. The ml possible value would be 0. Then the ms could be plus 1/2, or it could also be a negative 1/2. I'm going to use a different color. We can also have n other than just L equals to 1. L equals to 0. L can also be a number 1, and ml could be negative 1. This is plus 1/2. Then we can have the same thing, but the ms value is a positive 1/2. We can then have a different color, 2, 1, 0, 1/2, 2, 1, 0, positive 1/2. And I'm running out a little bit of space here, so I'm going to zoom out a bit so I can fit an extra stuff. And the last one that we can do is 2, 1, positive 1, 1/2, 2, 1, 1, negative 1/2. And if you count all of them, you can find that there's 2 s orbital, which means L equals to 0. And you can also find that there's 6 p orbitals. All right, so that's just kind of an example. Let me zoom out a bit. And if you want to copy this, then you should. But otherwise, we're just kind of matching all the possible rules. We're going to go back out to page 29 here and just kind of put both concepts together. And what it is that if you forget the rule, then you can look at the periodic table, and as long as you remember how they look like from one to the next, you should then be able to derive the rules again. Because the periodic table is more or less arranged in this particular fashion again. So we've already established from our earlier kind of permutations of all n equals to 2 that there should be 8 of them, and you should find that there's 2 s orbital as well as 6 p orbitals. Right? So that's essentially what we have here. And essentially the best way to think about them is that you have s orbital, which is L equals to 0. Then you have ml equals to 0 and 0, negative 1/2, and positive 1/2. And when we get to the p orbitals, we have L equals to 1, negative 1, 0, 1, negative 1, 0, 1, and the rest is the same as well. Right? So they're pretty much the same, except the periodic table, which there's an additional rule in the periodic table that I do want you to notice here, is that there's a little bit of a shift. That is, the first s is perfectly fine, it's linear. 2 is linear, but once you get to 3, it actually shifts by 1. This is shifted by 1. And then it goes back up again. Right. And then when you go to the next one, so essentially we're shifting these ones. Obviously, there's another table here, which is the lanthanides and actinides. They're actually shifted from this particular point. And usually in your periodic table, there should be a little bit of a line that tells you that they're shifted. And you can look for from that as well by looking at the atomic numbers. It's going to jump down there. Most of the time, you're not going to be working with actinides and lanthanides unless you're going to go into radiology. And we're not going to focus too much on that because the rules of these really, really high number particles, atoms, are just a bit weird. They behave even weirder than the d orbitals. So we're just going to mostly, in this class, focus on the one that's very, very common, which are the ones on this block, as well as a couple rows in the d block. But that's a little bit after this particular chapter. So my point is that if you forget about the rule, then look at the periodic table. If you remember kind of how they're arranged, there's 6 p orbitals, then that means there's 3 different ml, right? Because essentially you have to divide the numbers by 2 and so on. Okay. All right. Any questions so far? The rest is it's a rule. You kind of have to memorize the rules. There's a lot of rules that we're going to visit again and so on, but for now uh, we'll get to that as well as for today. The drawings is all right, so I'm going to skip that one, and instead we're going to kind of fill in some of these things as well. Now, the vernacular that we're going to use is mostly, we're not going to use that bracket thing with the 2, 1, 0, negative 1 over 2. That's not the most common way people talk about these orbitals, and instead they're just going to talk to you in terms of the common name, which is the s, p, f, and d orbitals, and so on. Right. So for example, in this particular case, when you have a 1s orbitals, this indicates that n equals to 1, and then L equals to 0, yeah, for s orbitals. For 2p orbitals means simply n equals to 2. Whatever the first number is going to denote the particular orbital, the particular shell, excuse me, or quantum number n. And then p orbital indicates L equals to 1. And same with the next one. So in this case, n equals to 5. L for f orbital is equals to 3. N equals to 1 and L equals to 2. So it's just kind of putting some of these things together. That is, p orbital is L equals to 1, f orbital is L equals to 3. Now sometimes, why don't we give them the name as they're formally named? Yeah, sorry. Oh, my bad. This does my hand work differently than my head occasionally. Actually, a lot of the time. But thank you. Clarification there. Obviously, the thing about naming these things and how common name prevail is because before the formal naming structure of N, L, and so on exists, what we have is experimental data. So what happens before is that when people look at the spectrum of these atomic molecules, what they see is more or less something that looks like this. So this is the energy scale, and then this is the intensity. And the first one that they see is a sharp peak. So it's sharp, so they call it S. And after the first sharp peak, they see a spectrum of a large peak that's quite intense. So, oh, we're going to call it, this is much bigger than that one, so we're going to call it primary, because it's the larger one. And then more experiments will happen, and then they find out it's like, oh, there's another energy spectrum, but it's kind of large and flat. So they're calling it diffused. And hence the SPD orbital for some of the most common one. That's more or less where the naming start to break down. Afterward, they find out that there's other things that are even more diffused and even kind of in a greater stretch. And it's like, all right, I have no idea how to describe this thing, and they call it F for fundamental, which absolutely makes no sense. And they realize like, oh, hold on, this thing is just going to keep going on and on and on beyond F. So let's just kind of keep going from S, P, D, F, and after F, we're just going to go G, H. And I think beyond those number, the energetic is way too high, it's not very stable, so we don't really concern about those anymore. So hence the numbering goes from S, P, D, F, then somehow it becomes alphabetical after F. That's just a little tidbit.
What's the word on the y-axis?
Intensity. So they're taking spectrums, and the intensity that they see more or less look like that. Hence the naming the name sticks, because sometimes it's much easier to say, oh, we're talking about the sharp one, so it's the 1s orbital is what we're looking at.
I have a question about
Yeah.
that. So in the book, it was saying so like how you would name something like it's 2s 2p, like to describe one of the elements over in the p block in the top row, and you say the number of electrons in each orbital. But they also shorthanded it to, oh, you can just write Hg for helium, and then
That's when we're talking about multi-electron atoms.
okay.
We're going to get that right in just a bit, but what we're talking so far for now is the individual orbitals that we're talking for each. That each of these corresponds to a single orbital. Hence, we're just kind of trying to try to name each of these individual ones. While that's actually a good point, and then we're just going to go in just a bit more, and we're going to skip some of these things. So how many electrons can exhibit n equals to 2? Then all you have to do is just count 1, 2, 3, 4, 5, 6, 7, 8. You get 8 and so on. So we can skip that a bit. And if you try to count all the possible permutations, you'll find that for n equals to 3, you're going to have 18. That is, there's 2 here, there's 10 on this side, and then there's 6 on this side, so you get 18, and so on. So that's, again, that's something that you can find and count from the periodic table as well. The last one that I think that I haven't actually talked about too much is what is the nature of this ms value. So we've already talked about the p orbitals. The p orbital tells us the shape, right? So for, let's say, ml equals to 1, there's 3 different p orbitals. We have the one that's pointing in the z direction, we have one that's pointing in the x directions, and we have one that points in the y direction. But so that so far only tells us the 3 different orbitals, and you can see that they're pointing at different direction. Hence, there's 3 different ml value, so that's a magnetic one. But how does the ms value comes into play for all of these orbitals? Right. For each one, there's actually 2 of them. There's a positive 1/2, and as well as a negative 1/2. So essentially, not all of these orbitals exist, and they can be occupied, but sometimes they're also going to be empty. So what happens is that when an electron comes in, and they fill in on these orbitals, they're going to first fill in one orbital at a time. So let's just say we're going to put an ms of positive 1/2. So one electron is going to come in, and the electron is going to make this particular shape, but as it spins around, the electrons exist, but they spin and spin and spin, and as they spin, they create this particular shape. And when we're talking about the ms value of negative 1/2, it's the electrons occupying pretty much the same orbital, but now it spins in the opposite direction. Hence, sometimes you can also hear that the ms values are clockwise and counterclockwise, although which one is positive, which one is negative is arbitrary. They just spin in opposite directions. There's 2 of them, and they occupy the same thing. Or they could occupy the same thing. Hence, each orbital's fits 2 electrons. But the point is that each of these electrons have a different state. One of them is, otherwise they're identical, except one of them is clockwise and the other one is counterclockwise. And essentially the same happens with the rest of the ms orbitals as well. One is spinning one way, and the other one spins in the opposite. So each of these consists 2, 2, and 2. So in the end, we have 6 electrons fits in the p orbital. Right? and so on. Any questions so far? Before we go on to the next portion, I kind of want to revisit some of the calculation because it's kind of important. I want to revisit the calculation for the energy, specifically for one electron atom. So if I have a hydrogen atom, where an electron goes down from, say, n equals to 3, and it goes down to an n equals to 2 state, what is the energy of the photon that is being emitted? Or I should say the energy of the photon, as well as the wavelength of the photon that is being emitted. Okay. You can answer it either in electron volt or in joules, but you can answer it in electron volt. So how do I calculate the energy of the photon first? What equation do I want to use, as well as how do I find out the energy of n equals to 3 and n equals to 2? Yeah, this is HV. Yes, this is correct, but not quite. This is true. This is the correct equation. Yes, is. We're talking about the hydrogen atom first here.
So it's going to be the change in energy is equal to the absolute value.
Right.
Of the n equals 3.
Right.
Minus the n equals 2.
Right. So that's kind of what I'm looking for now. This is true. This is still a correct equations, but in this particular questions, the way to solve it is, I have a hydrogen atom with only a single electrons, so I need to know what is the energy for n equals to 2 as well as an n equals to 3.
Is there just going to be a modified equation for when we deal with multiple electrons?
Yep.
Okay.
So how do I find out what is the energy for a quantum number n equals to 3, or any quantum number n, for one electron atom?
So it's the negative 13.6 electron volts.
Right. And what we're going to do next is we simply put in n equals to 3 for one of them, and then n equals to 2 the other one, as well as, because we're talking about hydrogen atom is defined as having only one proton, so z equals to 1. Right. Now, this is okay for now, yeah? There's a lot of equations, so just kind of know when to use one to the other. I suppose it doesn't hurt to just kind of finish off this particular problem, and then we'll just calculate everything all the way to the end. So it's a good practice one anyway. So the energy of the photon is going to be, I'm going to factor out the negative 13.6. It's going to be 1 squared divided by 9 minus 1 squared divided by 4, because that's 2 squared. And if we do the calculations, we should get in the end times 13.6. So this should comes out to 1.888 electron volts. If we put an absolute value in front of them. Right? So this is the energy of the photon, which is simply equals to the difference between the energy states of the two stuff that we're talking about here. And if we want to know the wavelength, it's kind of useful to just do 1240 divided by 1.88888. And in the end, we should get 656 nanometer in this case. So, just an example. Now, this is true for only a one electron atom. That is, if we have a hydrogen atom that's with only a single electron, that's fine. If we're talking about helium atom with a plus charge here, that means it only has, again, only have one electron. This equation is valid too. But once we get into multi-electron atoms, this equation no longer exactly valid. And we'll revisit that in a bit, but anyway. And then for a hydrogen atom at least, the thing that we say, oh, we're going to try to do n equals to 2 versus n equals to 3. Oops, I'm trying to erase this thing. It simply means that for a hydrogen atom, it's a transition from, say, an electron here, n equals to 3, into an n equals to 2. Right? So it's the electron moves from a higher state to a lower state in this case, and I'm trying to refer it back to the periodic table that we just talked about before. That's a bit of a refresher. I'm going to skip this one for now because it's the rule. I'm going to skip that for now. Sorry, I think I'm in page 31 now. Do you guys want to actually draw the s orbitals from the equations from the textbook, or not really? It's kind of fun, or at least fun for me, but it's not that great. If we have time, we'll revisit this, but I think there's better things to do than this. We'll see it again in a bit, but I'm skipping around to page 36, I think, is where we are. Okay, yeah. I'm going to skip around to page 36. If we have time, we'll revisit, and what I'm trying to get to is that if you actually try to draw all the equations that's written on your textbook into an actual shape, you will get more or less a shape that we've just drawn before. We're going to make it slightly simpler because we can't draw a three-dimensional structure in our head, or at least calculate it with the tools that we have with just a calculator. But if you do, then you actually get the same shape. What I mentioned before is that if we have only a single electrons on our atom, so let's just say this is the nucleus, so we have a positive charge or even multiple positive charge, and we have an electron. So the electron could be here, so it's n equals to 1. If we simply move the electron to another energy level, to something higher, so n equals to 2, then we simply move the electron upward. But what happens is that when you have multiple electrons involved in a particular system, so let's just say we have 3-electron system here, so only 2 electrons can fit in n equals to 1, and another one can fit in the last one, the shape is actually slightly different because now we have multiple kinds of interactions. We have electrons being pulled inward. Electrons are negatively charged, so they get pulled inwards towards the nucleus. So is I'm going to move the last electron there, so that just to give us extra space. Just make it a little bit smaller so I can have extra space there. So we have an attractive force of the electrons going into the nucleus. But what happens is that we have also an opposite force because the electrons and electrons repulse one another. They're like charges. So there's a repulsion between this electron with this electron. So there's some repulsion there. Maybe I should draw it a bit better. But anyway, there's a repulsion between this electron and that one. There's a repulsion between this electron and this one, and there's a repulsion between this electrons with that one. So essentially, all of these particles, charged particles, interact with one another. This gives us actually a huge problem mathematically. For the simple system of only a single electron, we can actually solve it exactly. So we have what they call an exact solution. So this is only one electron. We can actually derive an exact. And this exact solutions is what we refer to as the hydrogen wave functions, or sometimes also called the Schrödinger equation. So it's if you look at your textbook, there's a big wall of text. So Anthony, I think, are you in chapter 1? Yeah. The equation should be quantum theory, just a bit past this one. Like all of this is actually there's even more. So this is one of the solution for the wave function. You kind of have to combine both together to get the thing. That is the exact solution for a single electron system. As long as there's only one electron, it's perfectly fine. But once you add 2 electrons, mathematically it's much more complicated because all of these electrons are interacting with itself, and quite literally we can't solve them exactly. There's no solution here. So our mathematical language is insufficient to describe anything other than a single electron. So if we have 2 electrons, there's no solution. We can't derive exact solution. It's a problem with our own mathematical language that it's just not possible, at least. So, but we can make some approximation. So there's no exact solution, so it's not y equals to 2x plus b, but rather is y is approximately equals to an infinitely long series of stuff, and as long as you keep adding stuff to it, it gets pretty close, at least within the level that we can actually measure. So what happens is that we're going to modify the equation first from what we learned, which is exact. That is, for our exact solution, the energy of some atoms in some quantum number, n, is equals to negative 13.6 electron volt z squared over n squared. So this is what we have for exact solution for a single electron atom. But when we have a multiple electron system, we're going to try to simplify it a little bit by being slightly lazy and just kind of put this 13.6 electron volt. N is the same, so it's n squared. But now, instead of z, which is the number of protons that we have inside the nucleus, we're actually going to call this z effective squared. So usually I put it as z effective EFF. But z, or an effective nuclear charge. You see, because suppose that we have these 2 electrons, so we're just going to look at the 2 electron system here. And I'm going to redraw the nucleus here. Right? So this is the nucleus. So what happens is that the electron have an attraction force towards the nucleus. So this is, I'm drawing the attraction force in red. But what happens is that the 2 electrons also have repulsions against one another. So this electron here is being repulsed by the second electron up here. So there's actually a little bit extra force pointing outward. The same happens with the electrons over here. There's a little bit of extra force from the repulsion of the second electron, pushing it outward. So what happens is that this here is going to expand a tiny bit. So what we think about the orbital, although not exactly right, is actually going to expand just a tiny bit from what it was before. So it's going to expand a bit more. So now this is the new orbital shape. They kind of look the same, they behave the same, but they're not. They're just kind of shifted. And in fact, the more electrons that we have in the atom, the shift becomes greater and greater and greater and greater. But what happens is that it's going to get shifted. There's some electron repulsion between one to the other, and what happens is that it's going to make the atom, the electron slightly further away than we would like it to be. So we're just going to be kind of lazy, and instead of calling it the Z effective, there's actually, if this is 1 and this is a little bit of negative 0.01 or 0.2, then we're just going to call the Z effective as just 0.9 or something like that. And the concept is that the electrons are shielding one another. Sorry. But the whole concept is that we're just going to change the Z effective value here. There's a table that people tabulated from way back that for nitrogen atom, for example, the Z effectives are such and such. For heliums are slightly different because they don't have the same number of electrons and so on and so forth. You will get those numbers, or at least enough information to try to find them as well. But more or less, it's the concept remains the same. That is, if you have an absorptions or emission, it's the same thing too. The energy of the photon required for an absorption spectrum as well as an emission, it's just the same thing, which is delta E is equals to the energy of your photon. Now, specifically, there's 3 rules that governs in terms of the relative sorting of what energy is lowest and highest. There's the Pauli's principle. I guess there's only 2. No, oh no, Pauli and then Hund's rule, as well as the Aufbau. They're not really a rule, but they're just more like a trend. So, so here are the 3 things that's important. The Hund's rule is pretty straightforward. Electrons will fill the lowest energy first. So the best way to think about these electrons is just you have a bunch of stairways. If your electrons is here, it's just going to fall down to the lowest possible stairs, and that's where it's going to remain for a while. It's going to fall into the lowest energy first. The next one, it's kind of the same thing with this one. Preferably, electron will fill empty orbitals of the same. Sorry, can you cross that out? I'm just going to put the degenerate state. So sorry, that's kind of the second thing. It's actually just kind of an expansion of the first one. The electron will fill the first energy, the lowest energy first, energy orbital first. And then if you have multiple orbitals with the same exact energy, then it's going to fill in the empty first before doubling down on the same one. We'll get into more of the exercise, but we're just going to write it down for now. The next one would be the Pauli's principle. Essentially, no two electron can have the same state. This is where the ms value comes in. That is, if we have a state of a 2p orbitals, you can have two electrons fit in here. One of them must, however, spin clockwise, and the other one is counterclockwise. Right? So it's the same statement. No two electron can have the exact same state. These two states, the clockwise and counterclockwise, is different because one of them is going to have a plus 1/2, and the other one is going to have a negative 1/2. So they're two different things. And the last one is the Aufbau principle, which simply means which simply describes the relative energy between one to the next to the next to the next. So I'm just going to draw it, which is a bit easier. So I'm going to draw it from the bottom because this is going to be the lowest possible energy state. It's going to go from the 1s and then we're going to go to 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then of course we keep going and on and on and on. But the order goes something like this. It goes from this one first. So this is number 1. This is the lowest possible energy state. And then we're going to go this one. So this is number 2 in terms of the lowest energy state. And then I'm going to cross again. It's from the top, from the bottom up. So this is number 3, number 4, 3p, 4s, 5, 6, and then of course we have 5s here. What it is that it keeps going on and on and on and on. So this is going to be 7, 8, 9, and then we're going to start from the bottom again and just keep going up. Okay. So I'm just going to rewrite this linearly in terms of the lowest first into the highest first. We're going to start from the 1s, and then we're going to go 2s, 2p, 3s, 3p, 4s, so notice that it jumps, and then 3d, 4p, 5s. Right, so notice it kind of jumps again where these are located. Then we're going to go to 4d, 5p, then that's 5p, then 6s, and then so on and so forth. If you start filling in this whole table and just go ad infinitum, it follows more or less this particular thing. So this is generally true. This is the lowest state to get higher and higher and higher. This is generally correct. But once you get to large quantum number, for large n, more and more deviation. Because notice here is that the 4s and the 3d are switched, right? So if we simply look at the quantum number n, 3s, 3p, 3d, then 4s. So what happens is that you're going to have a little bit of mixing here. So sometimes, majority of the time, the 4s is going to be lower in energy, but sometimes it's going to switch. So it's murky. So is here. There's a bit of murkiness that they kind of just merge together. So it's true majority of the time, and that's because we don't actually solve it mathematically. Rather, we're just looking at the trend. So sometimes we just have to be satisfied with it's true majority of the time. And I want to kind of just bring this back out to the periodic table on page 29. So if you can flip back up to the previous one that we have, and you remember the order, the periodic table is actually arranged in that fashion as well, of the relative energy scale. Right. So essentially, if you go from here, you can see that this is 1s, and if you go all the way to the right, oh, actually, this is still 1s. So 1s, 1s. So the first one is 1s. And then if you keep going, you're going to meet the 2s. Then you're going to go 2p. Then 3s. 3p. And then we're going to jump to 4s. That's where we come back to the 3d, and so on and so forth in terms of the energy state. The Aufbau principle, if you forget about it, look at the periodic table. As long as you remember the s orbital is shifted by 2, and then there's going to be the f orbitals and the g orbitals as well. It's actually shifted by 2. So let me kind of clarify this again. The d block is shift by 1. The f orbitals are shifted by 2. I'll give you guys some assignment in just a bit more, but that's just kind of the point of it, is that the periodic table is organized more or less in the relative energy scale of the electrons. Let me go back to the previous page again. I think it's right here. Hopefully, way too far. Closer. We're getting closer. Getting closer. Okay, we're right here. So, so how does all of these three rules, the Hund's rules, the Pauli's principle, as well as the Aufbau principle comes in? Well, the Aufbau principle is just a relative energy scale. So the 1s is a smallest state. So 1s, 2s, 2p, 3s, 3p. So I'm just kind of drawing it this way. And notice that 1s orbital only have a single orbitals, and they can fit 2. Same as the 2s. And when we go to the 2p, there's 3 different kinds of p orbitals, the x, y, and z, and so on and so forth. So if we have 16 electrons, how would they stack up inside this particular system? And the best way to go is just kind of go from the lowest state first. So we're going to go spin up. So let's just say this is positive 1 over 2. Notice that we have to fill in the lowest energy first. So I'm just going to fill in the second electrons in the same box here. So we're fitting 2 electrons there. Then we're going to fit the next one pointing upward. The next one is pointing downward. So we put the first electron right here. So where should we put the next one? Well, these energy states are exactly the same, and they're empty, so I might as well just put stuff in the empty first. Note that I'm putting them in the same direction, arrows pointing upward in this case, uniformly. It's basically, these are, when your electrons are spinning, they have some magnetism associated with them. So essentially, you're just trying to line up all the magnets the same way, because otherwise, if you flip your magnet, it wants to flip backward. So we're just trying to line up the magnets correctly, or the magnetic spin. So we fill in 3 flat that way, and then the next one, we're going to flip downward. And again, we're kind of filling it on the bottom. The order is actually fairly important as well. And of course, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So this boxes here is just telling you how the electrons are organized. Some terminology. If you see only a single arrow pointing upward, it's called an unpaired electron, right? Because there's no pair. And these guys are paired electron. And since all those arrows tells you also how the magnets are spinning and how the electrons are spinning, and when the electrons are spinning, they create magnetic fields. The one that are unpaired are called paramagnetic, or I should say, yeah, just paramagnetic. Whereas the paired electrons are diamagnetic. And the definitions in each one is that the paramagnetic electrons are attracted to magnetic field, and the diamagnetic pair here of electrons repels magnetic field. More or less. Yes. Yeah, pretty much it is.
Why some things are magnetic and some things are not magnetic.
Right. If you have iron, for example, you'll see that they have a lot of paramagnetic electrons. So, and because of that, they get attracted by magnetic fields. If you put magnets on iron, it sticks. The other one doesn't. Now, unpaired electrons. Yeah. Now, obviously, you have atoms. All atoms have both a paramagnetic component as well as a diamagnetic. But what happens is that usually this diamagnetic term is usually much weaker compared to the para. Essentially, if there's a magnet, it repels magnetic field, but it repels it weakly, whereas when it's paramagnetic, it attracts it a lot more. So usually, if you have any paramagnetism at all, it's going to dominate the properties of your molecule. So essentially, these are unpaired, and essentially, whenever you see an unpaired molecules at all, they're usually referred as paramagnetic atoms or molecules and so on. But as you imagine, not everything is attracted to magnets. So majority of the object that we have out here, once we get to the molecular structures and so on, you'll see that wood and your body are not magnetic at all. When you see it, they're going to be entirely filled in. That's why they're not attracted to magnetic fields at all. One last one before I forget. Obviously, it's not really useful for us to keep drawing these boxes to describe the energy state of an electron. So there's a little bit of a shortcut, and there's even a shortcut to the shortcut. So instead of drawing it this way, sometimes you can also describe the energy state of the electrons by writing down, I'm going to use a bolder one here, 1s, and because there's 2 electrons in the s orbital, we put it to the power of 2. So it refers to that one there. Then 2s2, then 2p, and there's 6 electrons in the p orbital, 2p6, 3s2, and then 3p4. Right? So these 2 things are the same thing, so that's a truncated version of the top, and this is usually called as the electron configuration. I should say more specifically the ground electronic configuration. All right, so we'll take a little bit of break because I've been talking for about an hour. So a tiny bit of break, as well as exercise, so you can drink coffee, get some snacks while working on page 37. And then we'll revisit some of the energy calculations and so on in a bit more.